Alright, so this will be our first example of an improper, or, well, excuse me, an example of something that we'll use the integral test to address whether this series converges or diverges. So we have the series from 1 to infinity of n over the quantity n squared plus 1. I can actually look at this one right off the bat and tell you it diverges, not so much from just memorization and having seen it before, but it's going to turn out that there's going to be another useful test called the limit comparison test that you can use to show whether things converge or diverge. So, but we're not talking about that for now. We're talking about the integral test, but kind of a useful point. A lot of these series can be evaluated in different ways, showing that they converge or diverge. And sometimes some of them are much easier than other ways. So the idea here, again, we have to justify that this is a positive function, but that's pretty straightforward. I'm only plugging in positive numbers for n at the beginning, so the numbers on top are going to be positive, the numbers on the bottom are always going to be positive. So I think this is a case where you could say, hey, this is clearly going to be a positive function. It's certainly continuous, because what I'm going to do is I'm going to rewrite the portion of my series, kind of the formula part. I'm just going to replace n's with x's. So I'm going to rewrite this as x over x squared plus 1. And this is just a rational function. And remember that rational functions are continuous on their domain. The only thing that's left out of the domain of a rational function is anything that's going to make the denominator 0. But you should be able to convince yourself pretty quickly there's nothing that's going to make the denominator 0. So it's certainly continuous everywhere. All it really needs to be is continuous from 1 to infinity, though, again, because that's where I'm using my limits on my summation. So it's certainly continuous. That's not a problem. And now the next part is showing that it's decreasing. Well, you could argue, okay, as the values on the top get bigger, certainly the top's going to infinity. The bottom's also going to infinity. You could almost argue, since you're squaring the bottom, it's going to infinity faster, in which case this function should be decreasing. But you may be able to get away with that on an exam, but let's kind of show it the foolproof way. And remember to show that something's decreasing. This is where we use the first derivative test. So I'm going to take the derivative of this function, so f prime of x. I'm going to have to use the quotient rule. So it says I get the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom part squared. And remember, now you have to figure out where this function equals 0 or where it's undefined. Those again are the critical numbers. So if I simplify this down, on top I'm going to have x squared plus 1 from the first term, and I'm going to be subtracting away 2x squared. So x squared minus 2x squared is going to be negative x squared. I've got a plus 1, there's nothing over on the other side, so I'll have negative x squared plus 1 all over x squared plus 1 quantity squared. And you have to be a little careful. It's not like you can just cancel things out here because this negative's in here. What I am going to do is, well, I'm not going to do anything else at this point. I'm going to stop. You should convince yourself certainly the x squared plus 1 on top is not canceling out down here, because it's not x squared, it's negative x squared. So now I have to figure out the critical numbers of this. Well, again, that's where it's undefined. There's nothing that's going to make this undefined, because there's nothing that's going to make the denominator 0. And if you don't see that, you can always try to factor it, and this will not factor, which means there's no values of x that's going to make the denominator 0, which means there's nothing that's going to make it undefined. So that means I have to look at the numerator. And I'm going to rewrite the numerator as 1 minus x squared, so positive 1 minus x squared. And again, with a fraction, to figure out where it's undefined, set the bottom equal to 0. To figure out where it equals 0, set the top equal to 0. Well, this is going to factor as 1 minus x, 1 plus x. So that means my critical numbers are positive 1 and negative 1. So I'm going to make my little number line. Some people make a big chart. To me, that's cumbersome and it's time consuming on an exam. So this is going to be the sign of the derivative. And again, I've got critical numbers at negative 1 and positive 1, but all we really care about is everything to the right of 1 because that's where my index starts. So I don't really care what's happening over here at all. So don't even worry about doing that part. It's irrelevant for these problems. Well, again, it says you take a number larger than 1, you plug it into the derivative. If it's negative, it's decreasing. If it's positive, it's increasing. So maybe if I put 10 in. Well, if I put 10 in, remember I square it first, I'll get 100, but then I'll get a negative 100 plus 1. So the top is certainly negative. I'm squaring the bottom, so that's positive. So definitely I'm going to get a negative number for bigger than 1, and that means that my function is in fact decreasing. Okay, so I've got a positive I've got a positive continuous decreasing function, which means now I can turn this thing into its equivalent improper integral. And since it started at 1 to infinity, the limits, I'm going to start the improper integral at the same place, 1 to infinity. If this was 5 to infinity, I would be doing 5 to infinity. Again, I'm going to look at x over x squared plus 1. And now you're back to good old improper integrals. So if you've forgotten improper integrals, I do have another little video doing some examples of these, so it may help to take a look at them. You'll definitely want to be pretty familiar with them. And again, remember, you replace the infinity with a t. Well, t is going to infinity. I've got x over x squared plus 1. And now this is when my integration skills kick in. I've got to remember how to integrate this thing. Well, I've picked a relatively straightforward one. This is a u substitution problem. You can let u equal x squared plus 1. du is going to be 2x dx. So I've still got an x dx to replace on the top. So if I divide by 2, I'll have 1/2 du equals x dx. And I'm going to just kind of examine the improper integral, or excuse me, the indefinite integral. I'm going to forget the limits. I'm going to forget the 1 to t. So if I plug all this in, my x dx is going to be replaced with 1/2 du. And then I've got 1 over u left in the denominator. So if I integrate this, I'll get 1/2 the natural logarithm of u. But again, u in this case is x squared plus 1. And technically, okay, tag on a plus c, but that's not what we're doing in this problem, so I'm not worried about it. So it says this integral is going to turn into the limit as t goes to infinity of this stuff. I'm going to factor, well, I'll put it in there for now. You can factor the 1/2 out front. ln of x squared plus 1. And now I'm evaluating this from 1 to t. So I've got to plug in my limits of integration. So I'll have the limit as x goes to infinity. I'll have 1/2 ln of t squared plus 1. See if I can squeeze it all in here. And then I'm going to be plugging in 1, so I'll have 1/2 ln of 2. So minus 1/2 ln of 2. And now I have to think about, whoops, my t turned into an x. This should be a t goes to infinity. Now I have to think about these limits. Well, the limit as t goes to infinity, the inside of this part is going to go to infinity. And remember, as the x coordinates go off to infinity for the natural logarithm function, so here's y equals ln of x. As you plug in larger and larger x coordinates into the ln function, remember it goes off to infinity as well. Rather slowly, but it does go to infinity. So in this case, we're end up getting 1/2 times infinity minus 1/2 ln of 2. Well, this is just going to be infinity. And since our improper integral converges, that means we can now go back and justify that this original series also diverges. And now we're finished. So again, these problems can be pretty tedious. You have to show that the function's decreasing, which means, you're going to have to do all the derivative and critical number stuff and recall all that. Once you've justified that, now you've got, again, kind of the worst of both worlds. You got limits and you've got to do integration. The integration itself may be tricky. So you do the integration. At the end, you end up with a limit problem. The limit may be tricky. So there's a lot of places to kind of get tripped up here a little bit. But again, the basic idea, turn the original series into a function, look at the improper integral. If the improper integral converges, so does the original series. If the improper integral diverges, so does the original series.